day 5. And thank you all for coming through the strike to get here. I had to walk an hour to get here, so I'm sorry I'm late. But yeah, it's my pleasure today to finish everyone off by talking about the beginning. So I'm really going to talk quite a lot about inflation here. So there was a bit of a discussion about what I would talk about today. So Marco said that I was going to talk about, sorry? Oh, on the left? It's symmetric. Does it work? Can everyone hear? Okay, nice. Okay, cool. So there was some discussion about what I talk about. Marco said I should talk about the CMB. Misha says I should talk about DESI. We're supposed to be doing new physics from galaxy clustering, which I think restricts me to doing physics and data. So I'm going to talk about both the CMB and DESI, new physics in the CMB and old physics in DESI, and try and hope that sort of fits into this. But yeah, so let's start off by talking a little bit about inflation, just to kind of set the scene. So the kind of TLDR of all of inflation is we have a single field evolving with some potential, where fluctuations in that field, or if we like the Goldstone mode of broken time translations, set the rest of the dynamics of all of inflation, which is lovely. But the problem with this model is that it really has as many questions about it as it has answers. For example, what's the energy scale of all this process? Like what's the Hubble scale? What's the expansion rate? It could be 10 to the 15 gigaelectron volts. It could be much, much less. We don't really know. We don't know what this magic potential is, and we don't know why it's so flat. Furthermore, we don't really know much about the phenomenology of inflation. We don't know what sort of fields are active during inflation, and we don't really know if they interacted with themselves or if they interacted with other particles. So answering these questions is sort of complicated. For the different questions, there's different probes that you should look for. For energy scale, you should mostly look at tensors and B modes in the CMB, which I'm mostly not going to talk about. For the potential, you should try and talk to your string theory friends and see if you can learn something from that. For the other last two questions, this is sort of the regime where logical structure and the CMB can be quite useful. And essentially, this all probes into the idea of primordial non-Gaussianity. So, of course, how do we actually go ahead and learn about these specific phenomenological aspects of inflation? Well, the idea is this whole non-Gaussianity program, which essentially is all based on the idea that standard model of inflation starts with quantum fluctuations in a field, which ends up with classical Gaussian fluctuations in curvature. And essentially, any interesting thing you can do in the early universe that has some kind of nonlinear consequence, be it a nonlinear transformation, a nonlinear interaction, et cetera, generically changes this paradigm, and it changes sort of from a Gaussian thing, up here, to a non-Gaussian thing at the end of inflation. So non-Gaussianities in nonlinear effects in inflation lead to non-Gaussianities in primordial curvature, and as a result, if I have a way of measuring non-Gaussianities in primordial curvature, I can probe all the interesting, fun stuff happening in inflation. So what sort of interesting and fun stuff could we have? Well, let me just motivate this for sort of a couple of minutes by talking a little bit about in particular, different phenomenological things in inflation. So I should start with the sort of simplest, boring inflation once again. Once again, single field slow roll. If I simply go ahead and do QFT 101 in inflation, I can write down an extremely boring model for inflation with some action involving the field evolving in time and space. It's pretty boring. It's just two kinetic terms, and sound speed, etc. And if I was to do basic QFT with this, you'd find an extremely boring universe where a particle just moves somewhere in time and does pretty much absolutely nothing. Of course, when we do inflationary physics, we have to work slightly harder. We can't just do this nice Euclidean description. We have to actually work with proper inflationary symmetries and do everything in de Sitter space and worry about what happens to particles only sort of at the end of inflation when we see them today. So this little flat space 2-point function becomes this funkier thing in inflation. And essentially here you have nothing interesting happening at all. And because of this quadratic Lagrangian with quadratic interactions, you end up correlating the fields at 2 points in space at the end of inflation. Another way to say that is you have a power spectrum, or a 2-point function. So the nice thing about this prescription is you can then go ahead, kind of add more ingredients into it. And I think the first class of interesting things that could happen is that my field starts interacting with itself. So essentially in a Lagrangian picture, I can start adding in different sort of cubic or quartic or quintic operators into my theorem. Like I can start having 3 time derivatives, 1 time and 2 space. And it's basically any other thing I can write down consistent with the symmetries of the space that I've assumed. This is all super nicely formalized in the effective field theory of inflation, developed by several people in this conference, who definitely know much more about it than I do. But essentially the point is you have higher order interactions, and these lead to higher order non-Gaussianity. For example, this 3-point function at the beginning gives you a nice cute little Feynman diagram like this, which then correlates the field at 3 points in space, producing a 3-point bispectrum at the end of inflation. And the shape of this guy is basically informed by the type of interactions I assumed here. For example, this triple time derivative one, you can see this is totally symmetric. It treats all three fields in the same way. As a result, the bispectrum it creates is also totally symmetric. There's no preference for any of these sides as opposed to the other ones, so you have a nice equilateral triangle. Of course, you can do this with 4-point functions. This is when you produce G and L. In that case, there's 3 of them which are relevant, but only one of them turns out to be important in single field inflation for symmetry reasons. And once again, you have this single thing of they all produce some kind of inflationary shape with an amplitude telling you about microphysics and a shape telling you about the in particular vertex that I could write down in my theory. So of course, this is fun, but one of the nice things about inflation is anything you write down, there's always a bunch of things that you didn't write down but could have done. So the next thing you could write down is adding in not just self-interactions, but interactions with other stuff in inflation, in particular new particles. So it's fairly straightforward phenomenologically and much harder theoretically to do this with, say, multi-field inflation now. I'm sort of adding in an extra particle, let's call it sigma. We could have like interactions between my inflaton and my new scalar. It could be a, say, cubic order, this guy here, or quartic order, this guy on the right. These now produce very different bispectra and trispectra. In particular, these produce FNL and tau NL, local type. And there's a similar one you can write down with GNL, which is now a cubic instead of a quartic squared thing. Same sort of principle. The idea now is that the shapes you get here are a bit different. They're now extremely squeezed, which essentially physically comes from the fact that these legs are now sort of probing different things, and we have this sort of asymmetry here, one leg probing the wavelength of the intermediate exchange mode. So that's cool, but of course we can go even more fun, which is when we start getting into interesting physics with this exchange particle. It doesn't just have to be a simple boring scalar. In particular, what we could have is a new particle in the universe with some mass and some spin. And there's sort of a nice branch of research about this going back to kind of the early 2010s, and then really formalized and put into some nice catchy titles by Nima Akhani-Hamed and friends in 2015, called the Cosmological Collider, which is essentially saying that inflation tracks the exchange of particles with any mass and any spin up to some amount of considerations by some kind of diagram at the top here. You can just see two inflatons exchanging my new field. And I can predict the shape of this primordial interaction by just knowing a few fundamental things about this field. In particular, its mass, its spin, and also its propagation speed. In a particular kinematic limit, in particular the one in which this guy has much lower, in the correlated space, this guy has much lower wavelength than the other ones, or longer wavelength, though okay. I can predict the trispectrum exactly, looks like this guy at the top. Essentially the power spectrum of the inflaton itself times by the power spectrum of whatever you're exchanging in the middle, times by some functions depending on couplings, etc. And this is quite nice because I don't need to know anything about the actual microphysics of inflation. I don't need to know the UV completion of inflation, anything like that. I can just take these symmetries and then predict what the trispectrum should look like. So the whole idea of this is that it allows us to essentially use cosmological observables to learn something about extremely high energy particle physics. And it's very similar to what we generally do in a particle collider. So in a normal collider, we can't observe the Higgs particle directly, for example. What we can observe is the low energy stuff left over at the end. And essentially that's what we're doing here. We're inferring the presence of a massive particle by looking at the low energy stuff left over in the inflaton field or the distribution of perturbations today. So I should say you can also do this for bispectra. This is kind of fun. Sam was talking a bit about this yesterday. You essentially have this slightly different diagram when you now couple this to just one perturbation, sort of a hidden background leg at the end as well. This is sort of probing the same thing, not quite as generally. It turns out there's a couple of sort of slight differences here. This guy in particular requires this kind of linear coupling here, which generally is accompanied with this guy at the bottom, but you can break that in some scenarios. And it also assumes slightly more limited set of things. For example, this guy can only probe longitudinal modes. You have some weird inflationary particles and Giovanni Cabas and friends came up with one a couple of years ago that really doesn't produce bispectra, but just produces trispectra, you can essentially suppress the 3-point signal. So the real take home is that these produce both bispectra and trispectra, but if you really want to probe absolutely everything that could happen, you should probably try and use a 4-point function. Okay, so of course, inflation can do many, many more things than this. Other things that people could look for, but generally haven't, include folded non-Gaussianity, like bispectra, when you take the third leg here and sort of squish it towards the other ones, becoming this almost collinear configuration. That can tell you about modifications to Bunch-Davies vacuum and different kind of initial conditions for inflation. It can tell you about dissipation, sort of energy loss to thermal baths, and that sort of fun sort of stuff. It can also have things like oscillatory effects, sometimes leading to non-perturbative signatures that Paolo was talking to us about yesterday. Or I guess that was perturbative up to n=9, which is pretty non-perturbative. You can do extremely massive particles. I was excited about this recently, and things that can produce like 100-point functions, which you then see as a local signature in the CMB instead of one of these Fourier space correlators. Or you can start doing fun stuff with tensors by saying that inflation is not just scalars. We also have the tensor mode that we could, in principle, find with gravitational waves. I start drawing new diagrams when I now have extra legs corresponding to the tensor mode. And of course, there's ways you can make this non-Gaussian. You can start modifying gravity, adding masses to gravity, magnetic fields, gauge fields, et cetera, et cetera. There's all sorts of fun things you can come up with there. Of course, we've never actually detected the tensor mode itself, but it's not crazy to assume that it could also be non-Gaussian. There's no constraints almost at all on this, but this is just a sort of fairly brief summary of other things that could happen. Of course, with inflation, there's many, many, many more things that I didn't even list on this slide, but could still hopefully one day surprise us. So with all this stuff, how do we go ahead and measure it? So this problem ranges from very easy to very hard, depending on exactly what you're looking for. So the kind of standard way to do this is to look for everything in the CMB. And the nice thing is that the CMB directly linearly traces primordial physics, which means if you want to look for a primordial 3-point function, you just look for a CMB 3-point function, and that's it. With galaxies, of course, this is more difficult. Everything's nonlinear, which means a primordial 3-point function now generates a 2-point function, a 3, a 4, a 5, a 6, a halo mass function, etc., etc., which makes it a little more challenging and is partly the reason why most analyses to date are still done with the CMB. Okay, so CMB constraints have sort of evolved over the past couple of years. Kind of the standard state-of-the-art ones these days are the Planck official non-Gaussianity analyses. There's a beautiful set of 180 pages of Planck constraining stuff. They've mostly done sort of more of the template sort of style things of models which encompass quite a few of the actual physical things whilst being relatively simple to analyze. The standard three everyone loves are local, equilateral, and orthogonal, essentially massive particles of, massless particles and self-interactions, equilateral and orthogonal. And you get constraints. These are all numbers, all consistent with 0, which is nice if you don't like anything. So they do a lot of phenomenology. There's been interesting recent work just in the last year or two by Wuyun Sun and other collaborators in Cambridge, in particular James Ferguson and Paul Shellard, who've actually gone ahead and taken Planck data to go ahead and try and constrain some of these cosmological collider models for almost the first time at all in data, which was exciting. People are actually now sort of integrating these theory ideas in a practical context. And in general, every single conclusion from all these studies is that non-Gaussianity is small. So in natural units, FNL of order 1 is actually FNL of 10 to the 5, just because there's a factor of the square root of AS somewhere. And essentially, the constraints we get are much smaller than this natural bound, which means that the universe is, to a very high degree of accuracy, very Gaussian. Of course, we're still far from the actual limits of where we want to be here. Marco convinced hopefully most people that FNL of order 1 is a kind of made up number, but it would still be nice to get slightly closer to that bound. Right now, we're mostly at FNL of order kind of 10 to 50, depending on the different shape, with FNL local being constrained a little bit better. And in fact, the target for that is often quite a bit smaller in some cases. So this is kind of scalar 3-point function CMB. There's still a lot more to explore beyond this. And one interesting avenue of doing this is to start looking at the CMB as a way to constrain tensor physics instead of scalars, completely forgetting about the fact that we still haven't measured R from the CMB. If we put that aside, we can then go ahead and try and constrain tensor through-point functions, like I already mentioned. And the trick with this is that the CMB is measuring polarization. And for example, B-mode polarization traces gravitational wave helicity states, as does E-modes. So by concatenating, say, B, T, and T, we can measure cross spectra between scalars and tensors. And some recent work with Marisuke Shiraishi, myself, we sort of looked at every model of gravitational wave bispectra that we could think of and easily compute, which covered a whole spectrum of different variously well-motivated inflationary scenarios, massive gravity, viral gravity, etc. We got some constraints. Turns out this is actually quite hard. This is a little bit more challenging than standard inflationary things because of the shape of what these templates look like. They tend to be a little bit messy to compute, and it's very hard to explicitly separate them. Like CMB scalar analysis normally work by splitting up your bispectrum into 3 factorized pieces, which allows you to write down an extremely efficient estimator. For tensors, this is a little bit harder because you've got a lot of like tensor mode functions everywhere and polarization bases. Actually, Duivenforden did show that you can do most of this, but no one's actually attempted to do this on data so far. Yeah, Thomas. Yeah. Yes, all bounds in this entire talk are at fixed cosmology. I think that's probably not going to matter a huge amount. I mean, if you change cosmology, you're going to slightly change the template you're looking for in the CMB, but not by a huge degree, right? You could marginalize the other template and it's going to get slightly worse, but it's not I think in general, even if you got your cosmology slightly wrong, you would still expect to see the template if it was there. But you'd lose a bit of signal to noise if you weren't quite using the correct cosmology in the transfer functions. But it's unlikely that you just wouldn't see it because your omega matter was 4% wrong or something. Yeah. Okay. So these are kind of fun because when you start adding in B modes, you become limited by different things. In particular, the constraints on tensor non-Gaussianity end up being limited not by cosmic variance, but by CMB lensing and also noise in CMB B modes. And these are things that will get significantly better with time. We get better at delensing the data, and the noise from B modes gets significantly lower, specifically on very large scales, something like Lightbird, for example, if it flies. Which is nice because it means we can get these constraints like order 10 to 100 times better in the next decade or so, which is quite nice. Also, these constraints are mostly dominated by very large scales because of the particular shape of tensor transfer functions. For the same reason that CMB gravitational wave power spectra, measurements of R are generally done at like L less than, say, 100 or so, just because of the tensor transfer function shapes. But anyway, for now, the conclusion seems to be that non-Gaussianity in the tensor sector is small, as well as we find in the scalar sector. So this is nice, but of course we can go even crazier with our CMB analyses, and sort of the nightmare level of CMB analysis so far has been trying to do everything with 4-point functions. It drove me crazy for 2 years. And I think the kind of motivation for this is if you look at the Planck non-Gaussianity papers, there's about 170 pages devoted to bispectrum analyses and 6 pages devoted to trispectrum analyses, and 6 is much less than 170. So I decided to write 170 more pages. And until recently, essentially, we only have constraints on local type trispectra and self-interactions, in particular the 3 arising from the EFT of inflation, both in single and multi-field self-interaction levels. And that's kind of it, in contrast to like the hundreds of bispectrum models that have now been looked at. So there's really a lot more to learn here. And in particular, all of these constraints, I think with the only exception of tau and L, have only been looked at from the temperature. And especially as we look to future CMB data, we get a lot more information from polarization. So it's worth sort of building the technology to be able to use that in the context of non-Gaussianity. So let me say a little bit about actually measuring these 4-point functions and why I describe this as nightmarish. One of the complexities of actually doing this is to do with how you actually go ahead and measure stuff from the CMB. So CMB is a nice measurement of the temperature and polarization across all kind of 4 pi steradians of the sky, pretty much. And to compute the trispectrum, everything's linear, so all we need to do is take 4 measurements of the temperature or polarization and just correlate them together, and then just sort of integrate over all possible quadruplets of points on the CMB, just sum over all the tetrahedral configurations, if you will. There's two problems with this. Number one is that the trispectrum you can build has 8 dimensions. It has 4 phis and 4 thetas, or 4 Ls and 4 Ms. Even if I start adding in some symmetries, I can only really get this down to 5-dimensional once I include isotropy. And moreover, the total number of independent points on the CMB is of the order of 10 to the 28, assuming that Planck has around 10 to the 7 individual pixels. And 10 to the 28 points is quite a lot of points to add up. And you get kicked off your supercomputer pretty quickly, which is something I'm trying not to do. So how do we actually analyze this stuff? Well, what we essentially do is borrow techniques that are very common in signal processing and also very common in CMB bispectrum studies, which is to basically take your model, take your data, which is just the trispectrum measured at 4 points, multiply by some theoretical model you're interested in, and just integrate over absolutely everything. Sum over the entire CMB and compress it just down to one number. And if you do this in the correct way, you can essentially build an optimal estimator for any individual model you're interested in. Let's say I have a model of spin 1 mass 3/2 particle exchange. I can build the best estimator for that model, and I just go ahead and write it down like this, and then sum over everything, and I get out the answer, which is nice. So this kind of allows you to estimate directly the amplitudes of any models you care about, which is of course tracing inflationary microphysics. Actually computing it, however, is still slightly painful, because you still have a sum over 4 Ls and 4 Ms, which is still this sum over 10 to the 28 things. To do this efficiently, you essentially throw in every single trick you can think of. Low-dimensional integral representations, spherical harmonic transforms, Monte Carlo summation, random matrix tricks, etc. If you really want an extremely boring paper, I wrote like a 60-page paper about how to do this for various models of trispectra, which will send you to sleep pretty quickly. Anyway, the main conclusion is that if your trispectrum has some fairly nice properties, you can reduce the complexity of this sum from Lmax to the 8 to Lmax squared log Lmax squared, which is significantly better and actually able to do on a fairly modest supercomputer or your own laptop if you want to not use it for a week. Okay, so putting everything together, we can now sort of quickly estimate a lot of different 4-point amplitudes in ways that are fairly robust. They're not biased by masks, geometry, beams, lensing, assuming you know what all those things are. They're efficient to compute. They're technically minimum variance, like the best estimators you can write down, the general, public, all that sort of fun stuff. So now I should tell you a little bit about what we actually learned from them. So we basically throw all this methodology on Planck. You take the Planck temperature polarization, take some simulations, take some weights, beams, masks, transfer functions, etc., and a lot of testing and a lot of time, and then go ahead and learn stuff. So things we tried to learn included, of course, cubic non-Gaussianity, all these sorts of fun stuff here. And of course, I would love to say that we detected stuff. In that case, this guy would come and give me one of these. Of course, that didn't happen. We detected almost nothing whatsoever. It's a very depressing paper of trying to detect 33 things and not detecting 32 of them. The one we did measure, however, was CMB lensing, which was great. We can measure the CMB at 43 sigma, which at the time was the joint strongest constraint on CMB lensing ever, which has now been absolutely overcome by measurements with ACT and SPT, I think, as well. Frank Chu is the sort of person to blame, praise for that. This is a plot of the lensing power spectrum. Essentially, you can measure it and you get something that looks kind of like lambda CDM, which is good. It's not really a surprise because the CMB lensing people already use estimators which are in fact actually almost exactly equivalent to this kind of fancy optimal estimator trispectrum formalism, although derived in a slightly different way. Okay, so we didn't find any interesting things in inflation, and of course we can look at this in many, many different ways. One of the real motivations for this work was to try and do this with cosmological colliders, essentially to model massive and spinning particles that we mentioned before, which have some fancy shape involving sort of polynomial dependencies on mass of the field and angular dependence on the spin of the field. You can measure particles which have small masses, much less than Hubble, conformally coupled particles, heavy particles, etc. And you get out these corner plots of death, which I plot to you only there to show that you can do it. The other thing you should notice is that the little red blobs here are much smaller than the blue blobs. Red blobs have polarization, which just tells you that polarization is super useful. and ends up being even more useful once you go up to 4-point functions. Essentially, you have a huge number of combinations of T and E modes. So like a lot of the constraints here are driven by TTTT plus TTTE plus TTEE, et cetera, et cetera, et cetera. And of course, the constraints and all these things will very much get better. So what's next? What's next for the trispectrum? Of course, we can kind of add more data. We can just use our next favorite observatory, ACT, SPT, SO, et cetera, which provide data down to much smaller scales, which is good for some of these measurements. And in particular, polarization can help, especially for things like the tensors. And then the other thing is more models. There's a whole slew of different models, which I will not read out there. All of these can be constrained using similar methods. For some of them, it could be done in a week. For some of them, it could be done in a year. And some of them I still don't know how to do. But in principle, any other model that produces a trispectrum can be analyzed in a similar way or so. Whether we should do that is more of a sociological question. What I should say, however, is of course, the CMB is not really the optimal probe of everything. Of course, you all know that. You're at a large-scale structure conference. And I should now convince you that we should give up with the CMB and start doing LSS. And the reason for this is essentially that the CMB is fundamentally limited when it comes to measuring primordial non-Gaussianity. So future CMB experiments will only really improve FNL bounds by about a factor of 10. I think that's actually a bit over-optimistic. That was a number I stole from CMBS4 forecasts. This is for FNL that isn't FNL local. FNL local is a little bit more of an interesting case because you have this really interesting, strong, soft-hard coupling, which allows you to actually do pretty nicely. And essentially the reason is just we've already measured the CMB in every single direction. The only way to get better is to go on to smaller and smaller scales, which, as Manu, I think, convinced me, and hopefully many of you yesterday, is very hard. Got all sorts of problems of KSZ signals start popping up, which of course can be used as a way to measure this CMB, but measure FNL, but that's a sort of slightly orthogonal problem. In contrast, galaxy surveys are this sort of very rapidly evolving field. This is a little plot that I stole from one of Noah's papers and added some words to it. Basically to say this is how much information is in a galaxy survey as a function of redshift and time. Right now, kind of the state-of-the-art surveys that have been used for primordial non-Gaussianity studies are this little green dot at the bottom. See that by DESI, we end up getting to the top of this orange curve here, which is like almost 100 times better in terms of learning about stuff. For Spec S5, we end up doing significantly better. And importantly, we beat this red little band here, which is how well you could learn about Planck, just from a mode counting perspective. CMB is also a two-dimensional field, whereas large-scale structure is three-dimensional. That can help. Many models with interesting, say, oscillations in them, you end up damping this oscillation by projecting it out. So there's extra things you can learn here that shows up in studies like oscillatory power spectra, for example, and other observables, galaxy shapes, KSZ cross correlations, et cetera, et cetera. So how well have we done with large-scale structure so far? Well, so far, most of the analysis of large-scale structure has been done with BOSS, in particular, the BOSS power spectra and bispectra. So actually, to do this, we have to sort of jointly model both the power spectrum at one loop order, because of the first order loop correction encodes the bispectrum of the initial conditions. Take there's some sort of P12 contribution. Also the tree level bispectra, or other statistics that do similar things. For example, skew spectra. It's a nice work by Azadeh and Cora and people like this managed to essentially condense the bispectrum information into some nice power spectra and then use them on data to try and measure FNL. I think that was FNL orthogonal. So far, people have constrained FNL local from BOSS, as well as other observables as well. Marina gave us a nice talk about doing this for quasars. Dennis showed us we can do this for Euclid, which is great. And so far, in fact, the constraints are getting better with large-scale structure. So I think when we did this back in the Stone Age with BOSS, we got plus or minus 30. But now DESI people get plus or minus 9, which is pretty close, not quite the CMB, but we'll get there quite quickly. Of course, there's other things. We can start constraining equilateral three-point functions from self-interactions. This is a plot doing this for BOSS. It's a little bit of a busy plot, but the blue bands here are the constraints we get from actual data. Gray ones are if we're slightly more non-restrictive with our choice of bias parameters and we just marginalize over everything, assuming we don't know how galaxies work, which may or may not be true. Your constraints get a little bit worse here. Essentially, again, we detect nothing, but in fact, we don't detect anything, also not very well, but we're about 10 times worse than the CMB in this case. But then, of course, we can do even crazier things. At some point, Giovanni Cabas and the rest of the so-called East Coast team tried to detect massive particles in the CMB. In particular, we're trying to do very massive scalar field exchange. This was so bad that Matthias stopped writing cosmology papers after this. But it turns out you can try and measure these things, and for about a week, we were the strongest possible constraints on the cosmological collider until the CMB ones appeared a week later and were much, much stronger, which is not really surprising. But this can now be done. And I think any of these analyses on this slide can very easily be ported to future data, and hopefully with something like DESI, any of these constraints will become sort of order 5 times stronger. So one thing you might have noticed from this these slides is that LSS in general isn't very good. So they're about 5 to 20 times worse than the CMB in most scenarios, and that's basically for a few different reasons. Number one is the volume factor, which I already mentioned. Like just by mode counting, BOSS doesn't have many modes in it, so of course it can't measure stuff very well. But then there are other problems. For example, scale cuts. Like in general, all of these models are limited to models in which we can understand perturbatively. We can do, say, tree-level perturbation theory or now sort of one-loop perturbation theory efforts. And they're generally done with very few assumptions on any nonlinear physics at all, and say marginalizing over a whole bunch of galaxy bias parameters, etc. Moreover, they're normally done with very low-order statistics, for example, power spectra and bispectra, almost exclusively. So something I think this workshop's really emphasized to me is that you can go beyond basically all of these problems, which allows us hopefully to do better in the future. So for volume, of course, we just get better surveys. That's great. This is a little forecast for how well we can do for FNL equilateral from a stage 5-like experiment, megamapper. I know this has sort of been replaced by spec S5, but the constraints will still be sort of similar of this magnitude. This is actually a forecast of what would happen if we were to analyze stage 5 data with exactly the same theoretical treatment that we did for stage 3 data. So assuming that we don't get better at any level of modeling. You can see that the constraints we get are somewhat better than Planck, like a factor of 3 or so, better than the big blue Planck ellipse here. They're even better than CMBS4, which is great because we're not going to get that anyway. But SO would be somewhere between the red and the blue curves in this case. So of course we can in fact do better for the modeling. So Sam and Will both showed us kind of interesting ways to get models beyond this nice linear regime. So for FNL local, this is actually very promising. We kind of understand the relation between nonlinear physics and FNL local, just sort of locally changes sigma 8, for example, which allows us to model out to actually very small scales. Maybe that's something that can help. Maybe Will tell us about, or you can talk to Will about measuring stuff from halo mass functions or pairwise fun statistics, all sorts of things you could do in that case. And I should also highlight the sort of importance of assumptions on galaxy formation physics as well. So when we were looking at megamapper, we tried sort of doing a crazy thing of saying, we've got our forecast assuming we don't understand anything about quadratic biases in particular, so B2 and B tidal. And I said, well, let's see how well we could do if someone came down from heaven and said B2 is 3 and B tidal is 4. And it turns out if you were to know galaxy formation physics, your constraints on FNL would improve by a massive amount. In particular, these curves here, this is the constraint as a function of Kmax, and I should give the caveat here that we're being a little optimistic with our Kmax, as I think Jamie proved to us on Monday. But if we were to understand galaxy bias, the constraints improve by like a factor of 10 to 50, just by fixing these degeneracies in the data. Now, I'm not going to claim that we're going to know B2 and B tidal precisely by the age of megamapper or spec S5, but this is certainly a very active area of research, and like Misha's been very excited about using simulation-based priors to do this, and as of Guido and other people as well at this point. So this is certainly one area in which any additional information we add will of course shrink constraints like this one even more, and hopefully we'll finally at some point be able to approach the kind of interesting theoretical limits of maybe FNL of order 1, maybe with spec S5, maybe it will take spec S6 if they finally build one. And of course, the last thing is new statistics. So there's really a whole host of other things we could look at. A very incomplete list involves looking at trispectra of large-scale structure, which so far people really haven't done for standard inflationary GNL, TauNL, etc. With a couple of exceptions. We could look at the KSZ. There's correlations with CMB lensing. There's correlations with weak lensing. There was recently a sort of huge project of like simulating every type of cosmological collider bispectrum in weak lensing by Daya and Ambadjaga, etc. and friends. Galaxy shapes, galaxy spins, mass functions, etc., etc. So hopefully LSS will actually tell us something in the future. I would love to have finished this talk with a proof of how inflation works and detecting something, but unfortunately I can't. All I can say is that we will learn something with DESI, hopefully. And Misha told me I'm supposed to talk about DESI, so I'll just talk about it for 30 seconds to say DESI now exists. It's measured a lot of stuff. In particular, it's measured BEO parameters very nicely and given us excellent constraints on the expansion history that we all believe. Doesn't tell us about dark energy, maybe. It's also measured power spectra, which has been used to make some nice measurements of sigma 8. And right now, basically, the majority of the DESI papers have been looking at lambda CDM and its extensions. But I think there is a whole host of interesting stuff that can be done beyond this. There's been, I think, one DESI paper so far looking at FNL local, which is this plus or minus 9 paper, which is nice. And we're now in the point that the DESI data is now totally public. The year 1 release is all online somewhere, which means you can go ahead and do your own analysis with it. This is something that Misha, Anton, and I have been trying to do for the last 6 months. I couldn't find a picture of Anton, but this is what ChatGPT thinks he looks like. It's very hard to find online. So this is quite a hard thing to analyze, it turns out, because the actual DESI DR1 data looks like this table at the top. This is one of the samples. It's just a very long list of galaxy positions, redshifts, and weights to account for some systematic effects. And there's essentially no other data provided. There's no simulations, no power spectra, no covariances, no window functions, etc. So if you want to do your own analysis, you need to create all of these things yourself, which is quite hard. And of course, so we like challenges, so we try to do that. And we try to do this with the bispectra as well, which makes it even more complicated because then you have to account for systematics in bispectra. In particular, systematics like fiber collisions. Misha wanted me to give like 20 minutes talk about fiber collisions, but that would put everyone to sleep. But let's just say we now have some interesting methods for accounting for this sort of stuff, meaning that we can now sort of go ahead and do DESI bispectrum analyses. So the only kind of results we have so far are on lambda CDM. We essentially get constraints which are pretty comparable with what DESI gets, which is good. We're sort of analyzing the same data in a similar way, with slightly different changes on priors and adding bispectra as well. The constraints are slightly improved when we add in bispectra compared to the power spectrum ones, which is nice. That's fine. We detect lambda CDM. Good. We knew about that. There's a lot more to explore with this. Misha's talk, if you want some sneak peeks of things we're doing beyond lambda CDM, have a look at the talk. These are definitely sneak peeks. We haven't quite finished the analysis yet, and I think some things are still changing a little bit. But hopefully we'll have some constraints on, let's say, dark energy, curvature, neutrinos, all those sorts of fun things on archive in the next months or two, depending on once we get around to finishing them. But of course, there's a huge amount more to explore. So really, hopefully my talk motivates actually going beyond lambda CDM, etc., and starting to explore sort of primordial non-Gaussianity in DESI. Right now, this really hasn't been explored at all. Hopefully, DESI will start doing this for like the year 3 stuff. But of course, even FNL, the FNLs aren't enough. We could do colliders, we can do trispectra, etc., etc. And hopefully, with all this put together, one day we'll actually learn something. So on that happy note, let me summarize. Inflationary non-Gaussianity is great. There's a lot of things which can cause it. The CMB can measure it, but we didn't find anything. Galaxies also don't show us anything, and currently aren't likely to show us anything for a couple of years. But in about 5 to 10 years' time, we will eventually have the best possible probes of primordial non-Gaussianity with galaxies. So now is a super exciting time to sort of start developing that and allow us to hopefully probe inflation at its highest possible scales in the 5 to 10 years' time in the future. So thanks very much, and happy to take any questions.
So you think there's something that people, designing, specify, sort of, or, you guys get 5 times more galaxies, maybe, or 30% less quality?
Yeah,
Is this some
that's a good question, right? So I think from a lot of this inflationary side, you really just want to find as much volume as humanly possible. So, well, K-min drives FNL local. Every other type of non-Gaussianity that isn't local is driven by K-max, not K-min. Yes, yeah, exactly. Like if you can just measure a larger redshift range, like that's great. Yes, exactly. But you should only, so ideally, deep is, you only want to go as deep enough such that you become limited by like dark matter nonlinearities. Right? Like, for example, I don't know, Jamie showed us that Kmax for a redshift 4 sample or redshift 3 sample is probably about 0.2, 0.3. So ideally, from my point of view, you get as many galaxies such that you beat the shot noise down to about that level. Going deeper, it does not help, right? Because we're already limited at that point by modeling uncertainties. But going wider is great. So essentially, just measuring all the galaxies would be lovely, if we could do that. Yeah. Yep. Yeah, so this is kind of a classic systematic in Plunk is you have little point sources everywhere that give quite strong emission in temperature. So we didn't expect, well, within the analysis, you first of all mask out everything that looks like a point source, which means that once you've done that, you probably aren't going to have anything bright remaining, just because you can already see it. You run point source finders on Plunk to do this. So anything left would have to be a pretty small effect, and I think right now it's just swamped within the noise. For something like ACT and SO, you're getting a lot more signal to noise on very small scales, at which point this becomes a lot more relevant. Yeah.
With these trifecta templates you mentioned, various bits from template to template, how you compute at the end.
Yes.
But this, I mean, I guess for bispectrum, papers by person challenge.
Yep.
Question by. Is that also something that you do for trispectrum? Geometry.
Yeah, that's a great question. So it would be lovely to have a generic way of decomposing any trispectrum so that if you computed, say, one numerically, you could then project it onto this basis and just like go ahead and do that. The problem is it's much harder geometrically. The bispectrum is a function of 3 things. The trispectrum is a function of 5 or 6, in fact, primordially. And as far as I know, no one has ever written down a good basis for this. You have to be careful that the number of dimensions just doesn't explode very quickly. Right? Like 5 basis points for each axis is a lot once you've got 6 axes. Yep. In principle, yeah, I think as long as your basis is sufficiently flexible to capture the things you're interested in. For some of these oscillatory templates, that becomes less obvious. Yep. Yeah, to my knowledge, the real times when multi-tracing shines is primarily ultra big, strong signals on very large scales, which are really just FNL and TauNL, and I guess GNL. Not sure about GNL, but certainly FNL and TauNL. But these equilateral ones, no. I think obviously you gain from having more samples, but not to a greater level than that. Yeah. Yep. Yeah. Yeah, I just want to guess. Yeah, so I think there's very strong degeneracies between quadratic biases and FNLs, in particular these equilateral ones. And there's a nice paper discussing this by Dan Squared, Green and Bauman, maybe 2 of the Downs anyway. I think it's just physically they have very similar shapes. within the bispectrum, which means that you're limited by how well you can measure those from other parameters as well. For example, from the power spectrum, you do measure both of the biases, which helps a little bit. If you start adding in multiple traces, that will be great. The problem is each tracer, of course, has its own new parameters. And then the problem is instead of having 2 unknown biases, you have 4, etc. So I don't think it solves it that much unless you know additional information about those biases or about those traces. Yeah, this is sort of, it's a depressing thing, but it's not obvious exactly how to do it. Obviously, priors help, but then you have to be careful about, do these bias parameters then depend on FNL, which for example, with FNL local, we know that's very much true. That's where B-Phi and all these problems come from. Yeah. New data would be nice. I mean, new data, of course, is just the easy one, but that's a good question. I don't know. I don't love priors, but maybe priors are the best way to do it. Yeah, good question. I would love to have a good answer for that. Yes. Yep. Yeah. Yeah. Yeah, good question. Never thought about that. I'd say for lensing it, it's better than 10%, right? You get like, it goes from like, the lensing detection goes from 35 sigma to 43 sigma or something, which I guess is 20, okay, fine, 20%. I think in this case, I mean, you can show where all the information comes from, and a lot of it is just like cross correlations of temperature and D modes, and the fact that you have many different options to do that. Their T and E are not that correlated, right? So you get a lot of information. That's true. In terms of the transfer functions, I haven't thought too much about it. But, I mean, we know this is true for FNL as well. In this case, like for the scalar models, you can learn sort of additional 30, 40% by adding in polarization. It's not too dissimilar here. Yeah, in large scale structure or in CMB? I guess CMB, we do a joint analysis of both of the things at the same point, so you account for their covariance, which I think is the optimal thing to do. Yeah, that's true. Yeah, but for Galaxies, you can maybe do it, but it gets complicated, right? Because you have a lot of things you have to project out. You have to project out B2, the B2 piece, the BG2 piece, etc. The question of if you're going to lose all your signal when you do this, I'm not sure. It could be interesting to explore.
Okay, if there are no further comments.